Built environments are becoming increasingly complex in the horizontal and especially in the vertical dimension, stretching the limits of architectural design and of human cognition. Wayfinding, the basic act of finding our way from an origin to a destination, is becoming ever more challenging, posing a tangible risk of getting lost. Advances at the intersection of architecture, cognitive science, and computer science provide new ways of analyzing the effects of architectural design on human decision-making. How can architects leverage these advances to enhance the design of wayfinding experience in today's complex buildings? Our paper presents CogARCH, an agent-based simulation framework that incorporates BIM representation together with evidence from real-world and lab-based experiments to model, simulate, and analyze wayfinding by architecture. Hello everyone, my name is Michal Gath. I'm an architect and PhD student at the Chair of Cognitive Science at ETH-Zurich. Together with my colleagues, Dr. Leonel, Professor Ruth Conroy and Professor Christoph Holscher, my supervisor, I'm very excited to present to you our paper for SimAUD 2020. The title of our paper is CogARCH, Simulating Wayfinding by Architecture in Multilevel Buildings. I'll start with a brief overview. Wayfinding is defined as continuous spatial problem solving under uncertainty. To handle this uncertainty and support spatial decision-making, information perceived from the external environment, knowledge in the world, is reasoned upon by means of internal knowledge, knowledge in the head. Architectural configuration, features, and spatial semantics are fundamental cues that shape our spatial choice set. These are determined early on during preliminary design stages and could have far-reaching implications on occupants' wayfinding experience. The case of multi-level buildings poses a particular wayfinding challenge, stretching the limits of architectural complexity and human cognition. Finding one's way within these buildings may present various wayfinding challenges for both novice and experienced users, namely discontinuous and discretized visual access towards key building elements, multiplicity of origin and destination pairs, and non-intuitive program arrangements. In turn, occupants rely on fragments of perceived or stored information and simple heuristics to support wayfinding towards goals that are not directly visible. The incompleteness of perceived information may result in erroneous decisions, loss of orientation, confusion, stress, and frustration. Whereas architectural design is a powerful and fundamental instrument to guide human wayfinding in buildings, existing simulation approaches decompose the spatial complexity of 3D multilevel buildings into 2D graphs of isolated floors that represent walkable and visible space in 2D, overlooking 3D visual perception of volumetric space between floors. At the same time, these simulations simplify human decision-making by means of rational, unbounded agents that present optimal wayfinding behavior that does not comply with real-world observations. In the absence of an integrated simulation model that reflects both the cognitive and architectural complexity of wayfinding in multilevel buildings, architects are not necessarily able to foresee the ways in which their design decisions may result in suboptimal wayfinding behavior, whether intended or not. To bridge this gap and fully leverage the potential of architectural design to support wayfinding by architecture, the paper presents the development of CogARCH, a computational agent-based simulation framework to simulate wayfinding in multilevel buildings. The paper's main contributions are twofold. One, an automated pre-processing pipeline to generate a 3D hierarchical and semantically rich navigation space from a 3D building information model. Two, a parametric cognitive agent with coarse-to-fine model of spatial decision-making in a 3D field of view. The three layers composing the navigation space correspond to each of these decision-making layers, while the agent's access to each layer of the navigation space is bounded by its 3D visual field of view. A strategic layer supports agents' ability to apply simple search strategies and heuristics to approximate the location of non-visible destinations. A tactical layer allows agents to make local turn choices and move in the direction of the approximated destination. An operational layer allows agents to calculate an obstacle-free shortest path towards a visible target. To demonstrate the potential of CogARCH to architectural design, we perform a sensitivity analysis to evaluate variability in wayfinding performance across 3 multi-level building scenarios with systematically varied architectural design. Design variations control the degree of vertical visual connectivity between floors. Scenario 1 presents the lowest level of vertical visual connectivity with vertical circulation enclosed inside 3 concrete shafts. The second scenario presents the highest level of vertical visual connectivity as we replace the concrete enclosure of both circulation shafts with a glass facade. Scenario 3 introduces a series of small-scale atria to improve vertical visual connectivity between the first and second floor. We hypothesized that the building scenarios with higher level of vertical visual connectivity would result in more efficient wayfinding, whereby agents need to walk less to find their destinations. Architectural changes are specifically applied to the three-dimensional configuration of the building. We do so to demonstrate the need for a cognitive agent with a 3D field of view in order to capture potential effects these variations may have on wayfinding performance that could not be observed using a shortest path agent. Accordingly, we simulate both shortest path and cognitive agents wayfinding across tasks typical of novice occupants. These tasks consider 21 initial origin zones combined with one of 5 semantically defined destinations. Preliminary results that compare the average distance of both agent types across tasks have demonstrated CogARCH's capacity to capture significant variability in wayfinding behavior given architectural design variations applied to a 3D multi-level building. This finding stands in contrast to the significantly less varied wayfinding performance of shortest path agents sampled under the same scenarios. In addition, an analysis of kernel density applied to path points across tasks reveals that spatial movement patterns of shortest path agents were highly localized and show minimal variability across scenarios in comparison to more dispersed spatial search patterns exhibited by cognitive agents. Finally, CogARCH is a work in progress. Extending our work and validating our findings requires a validation protocol. To that end, we recently completed a VR experiment where we replicated the simulation experiments presented in this paper with 150 participants. Preliminary results showcased that participants' wayfinding was significantly more efficient in the glass condition, showcasing statistically similar behavior to that of CogARCH agents. Future applications of CogARCH aim to extend its cognitive agent to deal with prior knowledge of the building and processes of learning and knowledge acquisition. We further aspire to integrate other models of cognitive agents and establish benchmark cases for assessing variability between models against real-world and lab-based data. Concurrently with extending CogARCH, we aim to integrate it into simulation-based generative design workflows. Such integration would incorporate evaluation of wayfinding performance alongside other performance criteria to prune the solution space. Such an approach has the potential to introduce a much-needed occupant-centered perspective to future applications of architectural optimization and design automation.